All right, welcome to today's Zendo Reliability webinar. This is Fred Schenkelberg, and I got a little bit different screen this morning. And welcome back to a bunch of folks. I recognize their names, and welcome back again. A couple of people I don't recognize, so welcome. Hopefully you will find this one not too distracting. I've got, when I was setting up and making sure I could annotate some slides, my machine kept rebooting. So I tried about 5 different ways to get a workaround, and hopefully this one holds together because I ran out of time to test it. So apologize up in front of this one. But one of the things we do in reliability engineering, quality engineering, engineering in general, is we deal with data. Let's see if I can get my screen to change. That would be good. I guess I'll use this part, is we deal with data. It might be field data, it might be data from an experiment, it might be data collected and analyzed for us by a customer or from a vendor, but we deal with data. And part of the process of looking at that is representing it. We might do a bar graph or a histogram or a dot chart, or heaven forbid, a pie chart, which I've never really understood. There's all kinds of ways we can visualize data. And sometimes we actually create a model. And I know many of you have heard of physics of failure models. And those are complex, generally, not always, generally complex models describing in detail a set of phenomena or interactions or behaviors of a system such that you can predict what it's going to do. You can use the model to say, hey, this multi-layer ceramic capacitor, given this set of conditions, this geometry, and this thermal cycling, this chemical composition, this method of solder joint attachment, location on the board, amount of stress it sees, we can predict how long it'll last before it cracks. Or we could create a model that says, hey, we got some field data for the first couple of months for our product, and we want to see how it's doing rather than just staring at a stack of data, and we create a wide-well plot. And that's a regression model. And sometimes we're just trying to understand the relationship between 2 phenomena, and we might make an XY plot or a chart and do a simple regression on it. And so we create models as a way to see things that we can't normally see, or to create models. And I'll get into a little bit more about why we do models. Now, the underpinning of doing this work, of collecting the data and creating models, is so that we can either ourselves make a decision, yes, this part or product or material will last long enough in our application, and make a decision saying, hey, this will work or not work. We got to do something different. Or it's to inform other people in our organization so that they can make the proper decisions. Do we go with vendor A or vendor B, for example? And it may be part of the data analysis we do. Or should we offer a longer warranty or shorter warranty, or should, whatever. It could be decisions all across the organization that our data analysis and modeling work informs. So the short way of saying what we do in modeling, in regression analysis is important. And so let's leave it as that. And I'm just drawing a blank here. Yep, I am recording. I just had that panic moment if I forgot to hit the recording model. So let me open this up to the chat window. When do you know you've got a good model? When can you trust it? Right? Early on in my career, I thought the Mill Handbook 217 was a pretty good deal until I actually tried to use it. And I said, this doesn't make much sense at all, and did some more digging and found out that it's pretty bad. And so I kind of lost faith in that. Validated with field data. Yeah, Mahindra, that's a great way to look at it. When predictions and field analysis can coincide, right? Yeah, like in a simple linear regression, if I'm collecting data, say from a production line, and I've got this XY relationship going on, I create a model, and then the next data point comes in and it fits as I predicted. It would fit on this line. It would be somewhere where I expected it to be. Or it's a great way to validate it. But let's say you really can't wait until you get the next data point. You're in development, you're running a test. How do you know that your model's good? Yeah, engineering sense. I like that one, Andre. Andre Michel, or Mitchell, I'm sorry. But either way, and Nanny, R squared, we'll get to that in a minute. It's one of the measures or metrics that we often look at. Right? And I like the engineering sense, it's an issue with being able to get enough of a model that allows us to say, yes, this is good enough. And that's kind of squishy. That's not a hard and fast rule as to when a model is good enough for your particular circumstance or situation. So it's something to keep in mind, is that what's good for me may not be good for the person that needs to make the $1 million decision, right? They may need more evidence that the model is accurate or accurate enough. And so it's a part of this it's a long spectrum of, it's a rough guess, and that's a model based on our engineering spiny sense, whatever, spidey, and all the way to that we have a detailed, fully validated, fully vetted, fully understood, scientifically solid model that describes it in detail and is accurate to the 10th decimal point. We usually work somewhere way in between that, and usually I'm closer to it's a gut feel. We usually don't have enough data or enough time to create and validate our models. The long view of this is what many of you mentioned, is that when we have confirmation that the reality of the world follows what we expected from the model. Now, unfortunately, is we don't always have time to wait for that. So we're going to talk about a couple of ways, like R squared, that we use to take a look at our regression analysis or look at our modeling and say, yeah, we think this is good. And here's some evidence that suggests that we're good. And some of it's a little bit on the statistics side. Some of it is that engineering sense. And so we'll touch base on a bunch of these things. Right. So models, we use models for all kinds of things. The fundamental piece of using models is sometimes the data analysis we have, the collection of information we have, highlights that there's interactions or relationships among different elements of our system that gives us the results. One of the simplest examples of a complex system is if you ever tried to use humidity in calculations or in work. It's usually not what we're interested in. What we're interested in is how much moisture is being held in the air, how much water is available, water vapor is there, actually there. And because if there's more actual H2O in a vapor form suspended in the air, the corrosion process that water causes, or the issues that water causes with our products, accelerates. It's related to how much of that moisture is available. And it's related to the temperature, because it's a chemical reaction. So the higher the temperature, the faster that chemical process will work. And the higher the temperature, the higher the air temperature, the more moisture that a volume of air can suspend. So 85 RH, relative humidity, is not a fixed amount of water per cubic meter. It's related to how much moisture is suspended in the air, but at a specific temperature. And so that even though that's just temperature and humidity, we often use those terms, but what we really are interested in is how much moisture is suspended in that air, in the water content or the moisture content of the air, and that's dependent on temperature. And if we're investigating corrosion, well, that's another whole complex system that occurs. And so using various models of describing, say, corrosion rates is highly dependent on both temperature, moisture availability, surface roughness, all kinds of other things. Oops, looks like oh, thank you. Now I'm back. All right. Thanks for letting me know. I'm not sure what's going on today, but I'm having all kinds of different issues, and I'm glad I started checking early. But anyway, one of the ways we use models is to understand things that we can't typically recognize directly. So it may be a production line, it may be a product that has lots of interacting components and systems, it may be a material that reacts to temperature and humidity in complex ways or nonlinear ways. And so we collect data and we model this in order to get a tool that allows us to do what if analysis, it allows us to do predictions, it allows us to analyze accelerated data, all kinds of different uses of it. And part of that is then to also, well, what can we improve? What can we change that will make a difference? And if we move this dial on this machine, will it actually make a difference in the end product that we're creating, as an example? So there's plenty of different ways that we use models, and invariably they go back to us making decisions. It usually goes through data, then we create some information, then we get some understanding, and we may do some experiments along the way, and then we make decisions in the use of these models. Now, all of the models have all kinds of assumptions with them. And this is the part that has probably kept me in business for a good part of my clients' interactions, is challenging the assumptions. Years ago, I ran into a company that said, oh, we've got this flexible wristband. It's got some electronics embedded in it. And we know that bending electronics is not a good thing. Well, that was a good assumption. That was actually good engineering judgment, I thought. And so what they did is they flexed it from it. It was like a wristband, a circle almost, but it was not a closed circle. It not like a rubber band. But if you cut the rubber band and wrapped it around your wrist, and it held that kind of shape. So it was like a bracelet that you could slip on and off, but it would flex, it would open up and close. And so they would take the ends of it and extend it out flat. And then they'd let it spring back to its original shape. And then they'd spread it out flat. And the assumption was that by hyper flexing it, they would accelerate all of the motion that they would expect to see people using when they put it on and off their wrist. Now, I got to play with a couple of these devices, and there was all kinds of different ways to put it on your wrist or to manipulate this device, but none of them naturally occurred with this hyperflex. We're flattening it all the way out. And so the assumption they were making is that motion they were using was somehow related to the normal motion that it would see in use. But they didn't challenge that. They didn't check that. And it turned out that the motion that they were doing, even though it was a long, big flex, actually caused less damage than just normally using the normal twisting type of flex they did. Their machine kept it in a relative plane, whereas people would twist the device around the wrist. And so the twisting motion caused way more damage than what they assumed would be the most damage. But we also have assumptions that the models we use will be good enough, that they represent what's relevant in the system that we're trying to model. In the data analysis we have in the Weibull plot, we often make the assumption that what we're seeing in the data represents all of the failure mechanisms that are likely to occur into the future. And many of us have been surprised that, oh, in the 2 months from now, all of a sudden this new failure mechanism has created a whole new dynamic in the rate of failures. And we didn't see that earlier, but later the data became apparent. So our earlier model didn't include that phenomena. And we often assume that it does. And we often don't have an option. The data we have is what we have. Yet it's assumed that it's good enough. You know, what do the stock market folks always say is, you know, past performance is no indication of future performance or something like that. And so there's this rate of modeling that we do that has a whole raft of assumptions that we make, that it's got all of the variables, that the model is not missing any important relationships, that it's not too expensive to create or understand or model or to interpret. All kinds of things that go into it. And every one of the types of models in regression analysis we do has different sets of assumptions built into it. So one of the ways to help validate the check of your regression analysis is to detail out those assumptions that are being made, both from a statistics point of view and from just a physics and engineering points of view, is to understand those assumptions and make sure we're not validating anything critically important. And oftentimes it's a sensitivity analysis to help us understand that, well, if it's not quite normal, is that okay for what we're trying to do here? Or does it have to be really, really normal, for example? And we can check those kinds of things. Right. Many of you know, I think it's attributed to George Box. I found a variety of different sources for this, but you've all heard all models are wrong, you know, but some are useful or something to that effect. One of the things we've run into, even in physics of failure models, is that we can improve those models if we understand the distribution of all the variables that are going into it. Because not every capacitor has exactly the same capacitance. There might be a variable in there. It might be a uniform distribution or a normal distribution or some other distribution. But if we know that, we can use Monte Carlo techniques to incorporate that. But there's still error. There's still variations. There's measurement errors. There's material part-to-part variations. There's process variations. There's environmental and stress variations. There's some amount of, I want to say flux, but there's some amount of something going on that we almost never can get a handle on. And even if we go to the ultimate degree and measure and track and control everything, every time you use a pencil, the lead is dispersing onto the paper. And so your pencil is changing with every number you write down. And there's lots of other analogies or similes for this. But the basic idea here is that one way to make sure your model is good is to understand that it's not going to be accurate. It's not going to be perfect. And so the part of it is well, is it good enough for what we're trying to do? And we'll talk about some of those things. So what are your favorite models? I mentioned a few of them so far, but what kind of models do you typically use? And I'm thinking more along the lines of regression, where you're converting data into something. Linear models, those are my favorite too, especially when they work. RR/InSpec. Monique, what is RR/InSpec? Range regression, I'm not sure. Logistic model, yeah. Rank regression inspection upper point. Huh, I'm not familiar with that one. Multi-linear, multivariate linear models, okay, a little more complex. Surprised nobody's mentioned Weibull models. That's a model, it's a regression process. Okay, good, sure, all the time, yeah. Maybe it's just something we use so often that we don't think of it too much. Good, good. So good range of different things, different types of models and systems we're using. Good. Right. So errors, the thing that causes data to vary. Let me see if I can do a drawing here. Let me see if I can do something real quick. Let's say I have 2 points. I have a just 2 points. Let's see if I can get them to draw here. There we go. And I want to do a linear model. Well, there's only most every system, maximum likelihood, linear regression, rank regression, everybody else. Let's see if this will draw. Will probably fit a straight line through it. Of course, I missed. And get back to my mouse. Right, it'll go through it perfectly. Oops, grabbed the wrong thing. I've got too many things on the screen to perk. So imagine that that line's going straight through those 2 points. Most of our metrics, R squared included, will give us that that's a perfect fit. It's one of the things we learned when we first learned about linear regression, is we just need 2 points and we can draw a line through those 2 points and we can create a y equals, you know, x1 plus x2, or a plus b x1, you know, a plus x. We can create a linear equation for these 2 points, right? And the issue is that we don't have a way to check if there's any error or variability in this. We need a third point to tell if this linear fit is accurate for the system we're modeling, or if that third point we were, you know, what we're trying to predict, let's say it shows up over here. And the concept is that this linear line that we draw through 2 points assumes that there's a linear relationship between those 2 points. But if our third point shows up here, is that because there's a quadratic, there's a curve to our phenomena, or is it just measurement error? And so part of the issue is that the error is confounded or muddled with that it could be measurement error. It's just that our device that we're using to make the measurements is not accurate enough. And we've all run into that where we're measuring, say, the diameter or something with the caliper, and 2 different people will do it completely the same exact ball bearing, for example, will get different measurements depending on how you hold and manipulate the caliper. Now, if you use a better measurement system, more people will get the same answer or similar answers. But the differences between how 2 different people handle a caliper or 2 different measurement systems, the differences between those, is part of measurement error. And it exists with all the data that we have. In field data, a common error that we get is the customer doesn't send it back right away. All right. I was working with a product years ago and I thought we were doing great. And then one of our major customers sent back a whole pallet of products and said, we didn't want to ship it one at a time because we're getting too many. So we stacked them all up until we got a truckload and then we shipped them all at once. Well, when did they all fail? They didn't record that. They just threw them on the truck. And we ended up with a couple hundred units back that over the last 6 months at some point had failed. So we didn't really know when they failed. We just knew the number that were over some period of time. And we knew the serial numbers when they were shipped. But that was different than if the customer called every single time something failed and said, hey, unit XYZ just failed. Now we've got within a day or two, say, of the measurement system. Or even better is when you put systems in place on your devices that track the point of failure and what that failure was. But even that only works if it's actually tracking what's relevant, what's useful. And so part of what we do is based on measurements, or a lot of what we do in modeling is based on measurements. And we almost never account for that measurement error directly, because it's also connected with, let me see if this is my next slide, if I organize myself correctly here. Get out of that. Now I've lost my cursor. Here we go. Let me go this way. Oh, give me my mouse back. Come on. There we go. Is that the items that we make or the materials we use, the systems we create are not the same. And so there's going to be variability that occurs naturally given the interaction of our systems and models and equipment, or systems, equipment, materials, and so on, that they're going to be different to some extent. And generally that's controlled by our design, right? We're using this kind of material, this kind of manufacturing process, for example, so that we can get to within some tolerance. The problem is that unless that's really small, and if the measurement error is really small, we don't know which is contributing the variability that we're seeing. And so those errors in and of themselves aren't the complete source of variability in our models. And so we'll get into some of that in a moment. But the issue is that if we've got measurement error that's controlled, that's minimized, that's say less than 10% of what we're trying to measure, or the accuracy we're looking for, something like that, using that rough guideline, and that our part to part or item to item variability is also fairly well understood and stable, we're still going to have some variability. Now, we're not going to get around that. That's something that exists, and it has to be accounted for in our models to some extent, because if we have lots and lots of variability that occurs by measurement error or by natural variability, understanding what are the factors that are important to our model, right, are going to be really difficult to get a good value of. Our beta value in a Weibull analysis could be 0.5 to 5 if the amount of variability in our field data is really, really unknown, or very, not unknown, but very, very large. And part of that issue is that the lower our measurement error and natural variability, the clearer those other factors actually stand out. The things like dominant failure mechanisms, or the failure rate trends, or the expected lifetime in that distribution for our product in an accelerated test. If we've got very large measurement error, we're not going to see what's important. It'll be just noise. And to use that term, to mean that we have this fog around our data that doesn't allow us to see what's really going on. And so checking our systems often relies on that the measurement variability and the natural variability is minimized, is actually under control, stable, and small. And so before we actually start building models, it makes much more sense to make sure that our systems to measure and the systems to create our products are under control, to use an SPC analogy. Now, let's say that all works, right? We get a nice, clean measurement system. We get a nice, clean part-to-part variability. All of that is really nice. What should we expect? What kind of variability pattern should occur? And I'll open that up to the chat window here. Hopefully it's not just a stack of rocks out on a trail. So if I create say a linear regression, and I've got measurement error is contributing to the variability, and part to part, let's say I'm measuring parts on a production line, and part to part variability exists, and they're stable and in control, what pattern, how should those that variability behave? What should it look like if I looked at just the differences from the data I was collecting and the fitted line? Yeah, random. We here it would be a normal distribution, and random is a good phrase for it, but it's randomly taken from a normal distribution. If the measurement error is both plus and minus, it's not biased. And if our expected variation is plus or minus due to many small perturbations to the system, it should naturally fit a normal distribution. Not always, right? Some production lines clip the ends of the system, right? They have control systems that recenter a production line or a cutting tool or whatever once it drifts too far off the normal, the expected place. So some things don't actually create a normal distribution, but theoretically, if we are got a nice stable process and our measurement system is very clean, we should get a random distribution of those differences, those perturbations, from a normal distribution. Now, that's worth checking. And doing a normal probability plot is a great way to check if the errors, those differences, what statisticians call residuals, is actually normal. Now, there may be physical reasons why you wouldn't expect it to be normal. Maybe it's a basis of the measurement system we're using, or a basis of the nature of our manufacturing processes and things like that. For example, a product that as it ages, it tends to heat up, but then as it heats up, it tends to run at a lower bandwidth or lower speed in order to mitigate the effects of the extra heat. Well, that's changing the system as it ages, so that the errors early in the system, the measurements of its performance, for example, may be very different than its measures of performance later in its life, when it's accommodating some of the wear that it's seeing or some of the phenomena that it's seeing. And so there may be good engineering or reasonable reason or patterns to expect, but in theory, when you get a good measurement system and stable process, you should see in regression analysis, you should see a normal distribution of those residuals. And we'll talk some more about that here in a second. Yeah, and ideally, they're expected to be close to the regression line. And I agree with you, Monique, because that's a key part of it, but it's not the only thing we look at. If they're all right on the line, if I got 5 points and I'm fitting a linear line through it and they're all lined up directly dead center on that, I usually get very suspicious. Is that really what I should be expecting to see? Or is that made up data from some example someplace? It's very difficult to get away from the variation that will exist through the variety of different methods or ways that it appears. So in regression analysis, we typically pick up as many data points as we can, hopefully more than 2, but say 20 or 30 points. It is very rare that they'll line up in a perfect line. Even in a Weibull plot, right? We'll see lines, a tail at the upper end and lower end that will be slightly off. We don't worry about that too much because the 90 percentile center of the data set lines up pretty good with the data set. Yet, if you look at the residuals, what kind of pattern are they showing? What kind of distribution do they have? And that's part of the key, I think, to how you check the regression analysis, if it's good or not. All right, so let me get into some of this. So, and somebody earlier mentioned R squared, and there's two different R squareds. And as I dug into it some more, and I remember way back to my regression classes that, yeah, there are. R squared is part of a correlation coefficient. And the little r squared is for linear models, right? For the XY type models, or if something that you create a linear fit to. So we often manipulate the data and the plots for a Weibull plot so that it appears as a straight line. It's still a linear model because of the way we can do the analysis and a variety of other statistical nuances to it. But we can also get models that have multiple correlations and multiple factors, more than just an XY, but it might be 5 or 6 terms, and some of them are interacting and so on. And we can still come up with a coefficient for those. So capital R squared is kind of the general term of it, and little r squared is the more common one that we see for linear models. But it accounts for the proportion of the relationship between the variables. And I'll use the XY plot as the example. If they line up in a perfect straight line, R squared is 1, meaning it's perfectly correlated. If X moves by 1 unit, Y moves by, depending on the slope of the line, by a known amount every single time. But if it's just a cloud of data, it doesn't matter which line you put through there, they're equally bad, then R squared would be 0. Right. Oftentimes we're looking at R squared, and one of the issues with it is that when we're building models, when we're adding variables, let's say I'm looking at a Weibull plot and I get an R squared, this a value from it, or I'm doing a regression plot and I've got a number of variables that I can use to describe the variability, what's going on. If I add one more variable in a Weibull plot, I would go from a 2-factor like a beta and eta, and I add the gamma term to it, the location term, my R squared will probably go up. So by adding more terms, R squared can get better. And there's some variance to this and others that account for that phenomena, but it's something to keep in mind when you're comparing different distributions fit to your data. Generally, the R squared will pick the one that has the most factors in it. If it's a 4 parameter model, it'll get a better score, even though it really doesn't fit very well. Even though it describes more of the variability because it has more freedom to do so, but it's not actually a good model. So R squared alone is okay if you're very cautious about adding variables to it. Using it to compare different models doesn't really help all the time. You actually need to do something else in addition to just looking at R squared type stuff. Now, there's all these other ones that have all these different names of different statisticians over the years. And each one of them uses a slightly different way to go after how do you check a fit. Chi-squared, for example, looks at, well, I've got a linear model. It's, A plus BX, and I can calculate where the Y should be. And I've got actually Y data points, and I can compare those. And I make a comparison, a statistical comparison. Does this model describe my data? Or more accurately, does this model predict where my data should be? And you can do it, it's looking at residuals essentially, as you're looking at your data and where you expected that data point to be. And if they're too far apart from each other, then we can say, no, that's not likely from this model. It doesn't describe it very well. And chi-squared test we use for all kinds of comparisons like that, but it's used in regression analysis as a common type of tool. The Anderson-Darling and Kramer-von Mises, they use comparing the cumulative distribution function of a theoretical distribution versus the data generated distribution. And so the difference between these is the Anderson-Darling tends to weight the tails of your distribution a little bit heavier and then the middle of the data set, where the older version of this looks at all the data points equally, and so on. Each one of them has an ability to compare distributions, to rank order different things, to see how much variability it's related to, what kind of correlation, description does it provide. But all of them, all combined, still don't tell you the whole picture. They're all basically assuming that your variability from measurement error and that your model includes the appropriate factors or parameters is already there. And so how do you check, do you have the right set of descriptors in your model? Do you have the right distribution to fit your model? And there's lots of different ways to go about doing it. But these are some of the common ones that we see in different software packages. But when you dig into each one of these things, and whether it's through Wikipedia or your favorite stats book, each one has a set of caveats and areas where it works and where it doesn't work as well. Some rely on that you're doing maximum likelihood estimators, and that's what it uses to do the comparisons into the equation of it. Some are meant to be only comparisons. You have 3 different ways to create a model, and which one gives you the best description. Whereas others are just, how well does this fit the variability that you have? But none of them give you that warm and fuzzy, that trust that your model is good, at least in my opinion. Right. So one of the things, and I mentioned it a little bit earlier, is this idea of residuals. And so let me draw a quick line here. Oops. Let me draw a line, please. Let me do it up here. All right. So let's say this is on an XY plot, and I've got a handful of different points. Let me draw a line or a point, please. See if I can get it to draw. There you go. And one up here. Just to be random, I'll put one here and here. And so the nature of a residual is that it's typically defined as the vertical line on your plot. That's the difference between your model, the line, and where your data point is. And so it's this set of little differences, these vertical lines. And if I take this set and drop it on its edge and collect all the points, right, I should get essentially, a histogram. I'll just use lines. And if I do it right, and I have a good model, it should look roughly normal. Now, just like all of those other metrics and measures, residuals from a statistician's point of view also don't tell you, I mean, one of the comments is Monique mentioned is that they should be close together. Generally, close together is good, but right on the line, there's something else going on there, just from an engineering point of view. Is there something dampening or correcting the measurements so that they fit the model? Is there some phenomena there? It's worth checking if it's too close. There's not a guideline for how well this curve should be, right? How wide it should be, what's its variance. There isn't, from a statistician's point of view, if it's normal, that's good, right? And if it's not normal, there's lots of different indicators for what could be the problem. But the spread of this data is not all that critical. It just means you have a lot of variability in your system. And so it goes back to that point early on, is that you have to have a good measurement system, because that'll make this spread more if you have a bad measurement system, because you'll add that noise from your measurement system. And then if the process itself is creating products that are wildly variable, that'll create a bigger spread of this data here. So the absolute standard deviation or variance term of your residuals is not really all that important, because it's tied to phenomena that is beyond what your model can probably account for. And so that's the key point. This is what it should look like. And these are all those pieces that the model itself is not taking into account, right? We often put confidence intervals on things like this, and it's related to the variation of these residuals, essentially, but not entirely. It's related to more how well does this model describe the trend or the behavior of your data set. What's the appropriate model for it? The idea, though, is that if we got a good system, and whatever the absolute measurement error is or the absolute variability is of your system, is that if the model is adequate in describing the trend or the behavior or the relationship, it should give you a normal distribution for your residuals, right? But the absolute spread of it really isn't that critically important. It's more the behavior of it. So, and let me see if I can draw some of these in the next slide. I got a little bit more room here to go. Okay. So let's say I've got I created this model up here. I got 4 data points, and I want to draw these 4 data points, and this is my response. Oops, let me get the right tool here. See if this will work for me. This is my Y, and this is X. And that's X, and that's Y. Right. And so what I'm going to do is now, instead of the Y itself, I'm going to do the residual. So let me get rid of that. And so the first one's actually, and say this is my 0 line. So this first one is actually pretty close to the line. Next one is not too far away. Another one is up here, and then I'm back close again. Now, there's only 4 data points, so it's really hard to tell if that's normal or not normal or anything else. But let's say I keep running this experiment, I have more data points, and my next one comes up here, and then I get another one down here, and then another one here and here, and maybe another point up here and here. Is there anything wrong? Even though that when I plot the data back to say a histogram, it may actually be normal, but my residuals look like this, where there's this obvious trend. The higher the X, the lower the more negative the residuals, below the line residual. And when it's a low X, it's above the model line in general. Is that to be expected, or what could be wrong there? Yeah, some sort of bias, right? Maybe it's our measurement system that when X is on the relatively small end of the scale, it overcompensates for it. It doesn't measure it very well, or it adds some value to it. And when it's at a high value, it's more accurate and has a smaller or under measures it, for some example. Or we got the wrong model. Exactly right, Sean, is that maybe we're missing, maybe we should account for temperature. Maybe this thing is expanding and contracting, and the pattern that we use to measure these things, they change temperatures and they change dimensions. There's something going on here that has some variability that we should either control or account for in the model. All right, so let me get rid of that. Let's say I got a pattern. Here's my 0 line, and this is my run order. Right, this is this, say the order they're coming off the production line, right? And they start off tight, and then eventually my data points get really wide, so that if essentially my variability is fanning out as I continue to run the system. Right? Again, it's an indication that something's changing over time in the sequence of how I ran the experiment or made the measurements from the production line or gathered the data. So let's say I'm looking at serial numbers and I'm week of production, and my time to failure data initially is very tight, right, on my Weibull curve. But when I get out to 2 years, some of our units last a great long time and some of our units don't last hardly at all. But the variability in the reported times significantly increases and varies from our model. So if I'm trying to predict what's going to happen next month, I'm facing this increasing amount of variability. Now, it could be increasing amount of measurement error of when people report these things. Or it could be some phenomena within our production line that's creating the variability as products in our production line continue to evolve and change over time. So those are just a couple of regression or residual plots. Let me see, check my notes here. I know there's a couple more. Oh, another one is, so the ones I'm looking for is, one is that, am I getting a nice random pattern that when I analyze it, those residuals predicted versus the actual data, that I get a normal spread to this data set. That's what we want. But if I'm getting a trend, say they're high in one end and low in the other, or the variance is changing with time, those indicate that something else is going on that we need to account for in our system. I ran into this one. I had a product that was temperature sensitive. It was a heating cable that, as it got cold, it would generate more heat. And as it got warm, it would generate less heat. And so you could put an ice cube on 1 inch of it, and that 1 inch would heat up. The rest of it would stay cold. And it was a really cool product. It still is, as far as I know. But if you didn't control the temperature when you were measuring the resistivity of it or its capacity to generate heat, you would get widely different numbers. So we went to great lengths to control the temperature when we were making the measurements. And that didn't always work. And we had to worked on creating models to account for the difference in temperature. The trouble is that for products that weren't made correctly, it wasn't a simple linear relationship with temperature. So it created lots of challenges for us. The other thing we ran into, even when we had a pretty decent controlled room, and we're measuring, and this is just time, calendar time, our residuals in the springtime and the fall were very tight. So spring and fall, the residuals were pretty good. The temperature didn't vary all that much in our overall ambient, even though we had air conditioning systems. Those systems didn't have to work very hard to control the temperature to, I think it was 70 degrees Fahrenheit or 72 degrees Fahrenheit. But in the summer, another S, in winter, we had way more variability because it was much harder for the air conditioning system to control the temperature. And so we ended up with the cyclic behavior of our residuals. And so plotting expected versus predicted is one system. Plotting the run order of our products is another order. Looking at it calendar-wise, just seasonality is another pattern. But each of these kinds of things allows us to understand if there's something to be accounted for or adjusted for or incorporated into the models that we're using. And so my hope is this brief discussion about data and models and regression fitting is one, R-squared and Anderson-Darling and all the other metrics that we use to evaluate fits each have their own individual looks at the process and can tell us a piece of it. I think of it more of you can use a whole pile of these things, and it's similar to the blind wise men each touching a different part of an elephant. They will each get a different impression of what's going on. And even collectively, they're not as accurate or as not accurate, or they're not as informative as a residuals plot. And so between the residual plot and the the normal probability plot or Weibull probability plot, let's see, this would be, I think it's some variation of the CDF for the normal, some funky scale on this side, and then your run order here. If it tends to fit a straight line back to that linear regression, then you can have some evidence that it actually isn't the data that you have is from a normal distribution. But also look at the residuals. You know, are they exhibiting some behaviors or some phenomena that would indicate that something else is going on that you should either adjust for or account for? Now, my last piece of advice on fit evaluation comes from my regression classes I took in grad school, was that you take a 8.5 by 11 sheet of paper, or if you're in Europe or rest of the world, I think it's called an A4 size paper, maybe it's A2, whatever, roughly 8.5 by 11 inches. And we used to get normal probability plotting paper, and you can get Weibull plotting paper and other types of scales on these things. And they're usually about that size. Plot your data, fit a straight line through it. If it's a regression, print it out. And if I should change the color here, if a number 2 wooden pencil fits over the bulk of the data, say, and he didn't nail down whether it's 60% or 90% of the data, but if it fits over most of the data, it's a pretty good fit, right? So our judgment, our ability to look at a line and look at the data and say, yeah, that fits, is sometimes very obvious. We got a regression line, but our data does this. Well, we know we're not fitting that very well, even though the R-squared might be really good, or you know, or some of these other metrics might be say this is perfect. One of my favorite examples, if you have a data set that looks like this, has one far out point in a stack here, a line through this will give you a pretty good fit, even though it doesn't describe all this data that's here. So I could go on with all kinds of examples, but the idea is do the probability plotting, see what it looks like, do a histogram and some regression plots by run, by order, by season, by time, by predicted versus the actual. Take a look to see if there's any obvious patterns there. Now, of course, this only works if you have more than 4 points. Ideally, you have 20 or so points. It gets more complicated when most of these points are censored, right? If those things all don't actually exist, but they're just, we know that they existed up to that point but haven't filled, then I still have sparse data for this residual analysis. So it's, while it's not perfect, when you're betting a lot of money on decisions that are being made for your modeling results, is checking the model's assumptions, making sure you got good measurement systems, all of the due diligence up front, and then looking at the residuals and the probability plots allows you to get a pretty good sense whether you have a model that describes the data set that you're trying to describe, or if you've got a description of the system that works. Oh, and one last note, and it came up early on, is that let's say I create a model. Let's say this is a Weibull probability plot, is time. And the question we got is, what are the failures going to be in the next month? Or over the next period of time? How many failures should we get? Does our regression accurately predict what comes next? And so it takes time. It takes a while to do it. It takes a gamble that what our customers are reporting is going to fit with our projections and so on. But any of the models, that's a good way to do it. Now, if you've got the opportunity to do a set of experiments and you're collecting data, we'll leave, say, 4 or 5%, if you have enough data points, leave some of those data points out of your model. Create the model and then add back in those points and see how close they are to where your model would have projected them to be. So there's a couple of different techniques for doing it, but probably get into future topics here. But so let me wrap it up there. There's a couple of ideas. Hopefully I left you with a couple of notes. Regression analysis is actually very, very simple to do. It's the difference between your model and the actual, and then plot it in a variety of different ways. Unfortunately, some software packages don't make the residuals obvious or easy to get to. So it might take a little work depending on the package you're using to get to those. Probability plotting is almost always readily available, easy to use. Let's see. I have to get back to my cursor. Oops. And I got drawings all over the place. All right. So thanks everybody for showing up today and sticking with me, even though, and I'm glad my system stayed up the whole time. I still have some troubleshooting to do to make sure that goes with it, but it's worth doing to have the discussion, and hopefully you take away a couple of ideas. Is if you've got an R squared or any of these other fits, that's not the end of the story. You need to check it. Lots of different ways you got to play with that. And so finally, thanks for showing up today. Next month, Greg Hutchins is going to be doing a presentation on risk management and assessment techniques and different frameworks or risk management framework. Hopefully within an hour. It's a lot of topic there for him, but he agreed to do a webinar for us. That'll be next month. In a couple of weeks, Chris Jackson's doing one on how do you deal with expert opinion. And I'm sure I'm getting that wrong, but how do you account for that in your modeling and in your decision making? And so look forward to those, and we'll look forward to having you all back again. Thanks for running a little long. And Grace, I do have a PDF of the slides. I'll put those up with the recording, which will be on Ascendo Reliability underneath the webinar section, and should be up in a day or two. Hopefully get it there. And if you don't see it, or if you want to, just send me an email and I'll just email them to you. They're not that big. And my email is there. All right, so let me go ahead and thank everybody once again, and we'll end the sharing here.